Go for it.
Okay. Everybody probably has to check something that says, yep, I'm recording is good. And if you have multiple people there, that's great. I have no problem with that. The other thing is that when the time comes, if you have not, and I wanted to point this out, if you have not signed up for an exam yet and you want to take an exam on Friday, I haven't looked at the list today, but I do have access to the list. That is a separate sign up. You have to sign up with the FCC, and you have to sign up with okay, right now we have what looks like 18 people signed up for the exam on Friday. That's going to be 2:30 p.m. Pacific time. Although actually it spreads out a little bit because we have a lot of people to test. So we can only do like 3 or 4 at a time. So it'll be a little longer than that. But if you would like to do that, now is a really good time to sign up, or pretty much any time in the next, couple days. And the exams are done online with a group of 3 or 4 volunteer examiners who will monitor your exam, for which you use a webcam, just like the one you're using right now, and a second camera, such as on a phone or an iPad or something like that.
I had a question about that.
Yep.
It sounded like it wanted me to set up, like, I could just maybe use 2 computers or something, like
You
set
could
up
do
my
2
laptop
computers.
and then my
That's fine.
laptop or something.
Yeah, you could use 2 computers with webcams.
Okay, and it'll just be like a couple different Zoom links or something.
That's exactly what it is.
Okay, thank you.
You said it might take longer. So how big a time block do you have to arrange for to take the? Because it won't be just 1 hour, 2:30 to 3:30.
Well, there's no time limit on the test.
No, but you said they couldn't do it all at once. So what does that mean?
Well, that means we'll stick around as long as necessary to get everybody done. And what'll happen is if there are people who need to go first, we'll probably ask for, who needs to go first and schedule. And Kent, who runs the Anchorage Amateur Radio Club VEC, he will call people and get them up, get them on the phone and make sure they're up and running and all the technology's working. So
what do you mean a second camera? I mean, do you have to hold up your phone while you're talking to your laptop?
No, you typically just like put it up against a stack of books or something.
And prop it up so it can see you.
Exactly. Yeah. Okay. And so yeah, the first one is basically what we're looking at right now. If you can see your face on the screen, that's the first camera. The second one is just a second one, and we would typically aim it at the screen, or the combination of the screen and the keyboard and your hands, so we can see what's going on the screen.
Well, back to the time to block out for this. I need to kind of know, for the other people who might not want to come through my room, what kind of time schedule am I having to set up for Friday? How long a block of time has to be available?
Well, that's true. And if you want to go first, at some point, Kent is going to drift through, hopefully. And we can work on that. The other thing is, yes, you have to make sure that nobody comes into your room during the time of the exam. So wherever that happens to be, some people actually use a bathroom for that reason. And they just lock the door on the bathroom and put up a sign that says, "Don't bother me, I'm taking a test." And then if you have to go to the bathroom, I guess you can just go to the bathroom. Normally, if you have to go to the bathroom, we have to stop the exam and restart it. So. All right. Any other questions?
Yeah, Scott, I was just curious. I'm an international student and I was wondering if I am eligible for taking the test.
You have a US ID, a US issued ID?
I got my social security number. So other than that, I didn't get any other license. I mean, any other ID.
Driver's license?
No, I didn't take it yet.
Let me think. So I would talk to Kent. So if anyone wants
Got a
to,
passport.
a passport, but it has to be issued by the US. The other thing you have to have is a US address, but
Should be able to get an ID card short of taking the actual driver's license test from the DMV. They'll just issue you an ID card.
so do you have a student ID?
Yeah, I have a student ID.
Okay, I would ask Kent and let me look up Kent's email address real quick, because this is something that I don't know the answer to. Okay, I'm gonna put it in the chat. Everybody ready? It's going in the chat. This is Kent. And
Okay.
he's in charge of the exams and what's necessary to do it. So if you have any questions about the examination process, he's the person to ask. And like I said, he'll probably drop in at some point this week as well.
All right.
Any other questions?
I don't have your email up, but it had a link to that sign up, right?
What? Say that again.
I said your email had a link to that sign up that you're referring to, the Kent Proctor's.
Oh, yeah, it did. Yeah, it was in the email.
I just bringing it to everyone's attention.
Okay. All right. All right. Any other questions? Okay, so that we get going, so
Wait,
that we can
sorry,
get going.
Scott.
Yeah.
I had a quick question. Are there going to be any study groups for the rocks? Those of us that are rocks and are here in Florence. I don't know if you guys are going to do any study groups or anything like that. That's why I wanted to ask.
Well, when you say study groups, how do you mean?
Like to go over a repository of questions and stuff like that. Like some people, like I'm weird. I'm an audio visual learner. So I'm here when I've gone over the entire material, the PDFs and the questions, I have to read it aloud for it to sink in my brain. I don't know why it works like that. It's just the way I work. So if there's anybody else who's like that, if they want to even get on Zoom and go over the questions and stuff like that.
Okay. Yeah, I don't know that there is, but you never know. All right. Any other questions before we go?
Hey, Scott, I just had one question. I'm signing up real quick for the registration. What is an FRN?
FRN
Do
is an FCC FRN. When you go to the Anchorage ARC website, there should be a link that says something like, how do I get an FRN? You basically register with the FCC. It's a federal, like an FCC registration number. And that basically goes with you. Your license is tied to it.
Okay, thank you. I was just signing up for the test on Friday as well.
Okay. All right. And the other thing is, if you're signed up for an exam and you know at some point that you're not going to be able to take the exam on Friday because it's a limited number of seats, let me and Kent know, and we'll schedule you for another day, and that'll open up a seat.
Is the Friday date fully subscribed?
I think there were still some open seats. I think it was 18 or 19, and we have room for 21. So
Scott, will there be a course later on for the regular licenses versus just the tech license today?
what, like the general? I've never done an extra class, but I have done general classes.
All right, thank you.
All right, you guys ready to go? Okay, here we go. So the first thing we're going to do is we're going to talk about the concept of a wave. And all right, can everybody see everyone see this shared screen? I hope. Okay, here we go. I
Just have a white background.
I love my whiteboard. Okay, so. Okay, anybody know what shape this is?
Circle.
A circle. Okay. How many degrees are in a circle?
360.
360 degrees. Okay. So how many degrees are in a quarter of a circle?
90.
90 degrees. Okay. So I'm going to call this line our 0 degree mark. The way that circles work, we're going to start at the 0 degree mark, and we're going to go around this way and this way and this way and this way, kind of like a bicycle wheel. And as we go around, our angle that we've gone through increases. When let's say that we're starting at this point, which I'm going to mark with a red X. Right? So as we go around the circle and we get up to this point, how many degrees have we now gotten through? 90 degrees. We've gone through a quarter of a circle. Okay, when we get to the green mark, we've gone another 90 degrees. So how far would we have gotten at that point?
180.
180. Okay. How about when we get to the blue mark down here?
270.
270. Okay. How about when we get all the way back to the red mark where we started?
360.
360. But isn't that the same as 0? It's the exact same place, right? It has two different names. So it has 0 and 360 degrees. It has two different names that refer to the exact same thing. Okay, so now what we're going to do is we're going to change this, and we're going to say, all right, we're going to make a graph where our angle that we've gone through in degrees is on this axis. So what are those interesting points? We start at how many degrees? Everybody? We start at 0, right?
Yeah.
Okay, what's the yellow mark? How many degrees?
90.
90, okay. And the green mark?
180.
180, okay. And how about the blue mark?
270.
270, okay. And then back to the red? We're going to call that 360. All right, so we've now gotten an entire trip around the circle. Now, okay, we're going to have to think back to the definition of a circle. A circle is a collection of all points that are the exact same distance away from the center, from a given point. Well, we're going to pick, in this case, a distance of 1. We're just going to say that our distance of the circle, our radius, is 1. This is known as the unit circle. Okay, this is known as the unit circle, which means that at any point on that circle, our distance from the middle is exactly 1 unit. Whatever that unit is, doesn't really matter to me. But now, what we're going to say is, what I really care about is how far up or down we are from that line. So looking at this is the positive side, and this is the minus side. We've defined that as positive and minus and negative. So starting at the 0 point, which is the red X, how high up above that line are we?
45.
I hope we're at 0, right?
Yeah, I didn't know if you meant where we were or that line you
Yeah,
drove.
right on that red X. How far above that horizontal line are we?
0.
0. We're right on the line. Okay, but how about by the time we get up to the yellow X?
1.
At 90.
We're 1. That's right. How about when we get down to the green point?
0.
0. And how about the blue point?
-1.
-1. We've gone negative. All right. Okay. Well, now we're going to connect the dots. Okay, this has a very special name, connecting all the dots. This is called a sine wave, also known as a sine curve, but this is a sine wave. Essentially, what a sine wave is a measure of how far up or down, because that's what the sine function is, how far up or down from the 0 line you are. Now, what's really important about this is that a sine wave shows up in nature all the time. Can anybody guess where we might find this?
In water.
Yeah, water, you have ripples in the water. How about anything else that spins, like big things that go around in circles? We're on one of them.
Planet.
Planets, orbits, things like that, right? If you were to look at the amount of sunlight that we have it actually goes like this. From season to season. That's actually a sine wave because the Earth goes around the sun and the Earth is tipped. So this would be summer and this would be winter. That would be a sine wave, and it actually follows that curve. And here's summer again. So if you look at this, where would that be changing the fastest? It would be changing the fastest right here. This would be known as fall, and this would be known as spring. So we are actually gaining and losing sunlight at the highest rate right now. The days are getting longer faster because we're right at this point. Because we are riding on a sine wave. So this kind of thing shows up all over the place. And it happens to turn out that this is also really useful too, because the way that machines work, anyone ever seen an electric motor? Hopefully, right?
Yeah.
All right. What direction how does an electric motor turn? Round and round and round, right?
Mhm.
Goes around in circles around a center point. So if you can actually have something that is sitting here that's going around and around and around, well, and you can have that make a voltage, it makes a voltage that looks like this because it's going around and around and around in circles. If you have 3 of them, you can have one that goes like this and another one that goes like this. And it turns out that if these are a certain number of degrees apart, that would be 120 degrees, you end up with something called 3-phase power. That's actually the basis of something called power generation. And what do we use power generation for, everybody?
Electricity.
Electricity, that's right. So this shows up all over the place. We use sine waves. If you were to measure the voltage coming out of your wall socket and put it on an oscilloscope to look at the picture, it would actually look just like that. So sine waves are very important. And Jan, I would like to thank you for making me bring this up because I had never thought to do this before. I hope that made sense. Did that make sense?
Yeah.
Good. Okay. Okay. So now we're all on the same page as far as what a sine wave is. So,
But wait, can you go back to, you have it circled, you have the degrees of the circle, and then you made a leap to put those degrees out on a flat line.
because
Can
I
you
wanted
go
to.
over that step once more time? How you got from the circle to the flat line?
I just wanted to. I just basically, I just said, okay, I'm going to take the amount of the number of degrees that I've gone, and I'm going to make that my x-axis on my graph. Because I can. So it's just a graph of position versus angle. And this actually is going to become even more evident as in a minute, because if we have not just angle, if we can say, okay, well, this thing is spinning around in a unit time, well, then this not just becomes angle, this is time. And the faster this thing spins around, the shorter the amount of time that's necessary to get around one full time. And actually, that is the next step that I had actually written down to cover. So let us say that this circle, we're riding on this dot on the circle, and the circle, let's picture this as a merry-go-round, right? And we're planning on getting nauseous riding this merry-go-round. And we start at the 0 degree mark, and it takes a time of 1 second to spin all the way around on that merry-go-round. Right? Well, how long does it take for us to make that picture sine wave?
One second.
1 second. That's right. This is known as a period. Well, it's a period of time. That makes a lot of sense. Well, now the next question is, How many times per second did that thing spin around?
Once.
One
One
second.
time, that's right. And that would be known as a frequency. So that happened one time per second. And as it turns out, the unit of a time of a thing, I'm not going to use time, I'm going to use one thing, because it can be anything. Per second is known as a hertz. That is the unit of frequency. And that's basically that's named after Heinrich Hertz, who was one of the early discoverers and experimenters of radio. Okay, so now what we're going to do is we're going to take this and we're going to mess it up. We're going to say that we're on this merry-go-round, and now we are trying out for NASA's space program. We want to be an astronaut, and we're on this merry-go-round, and now it goes around at a rate of 10 times per second. How long does it take to go around one time?
1/10 of a second.
That's right. So our period is 0.1 seconds. Okay. And what is our frequency? How many times does it spin around per second?
10.
10. And the unit of frequency is?
Hertz.
Hertz. That's right. So now let's take a look at our sine wave. If we were holding a flashlight, how long would it take to carve out that picture, that beautiful looking curve on the right-hand side? How long would it take for us to make that?
1/10 of a second.
A 1/10 of a second. So 0.1 seconds. And how many times, if we were to look at that, how many times per second would that picture be made?
10.
10 times. That's right. So that would be 10 hertz. So what this means is that notice that we have these things that are inversely proportional to each other. As our frequency goes up, what happens to our period?
1 second to spin around.
Goes down. They're
Goes
inversely
down. That's
proportional.
right. They are inversely proportional. And what is the one thing that relates the two? What relates the two?
The circle they're spinning in?
That's right. And how fast the circle is going. If the circle is going, if that merry-go-round is going around very, very slowly, how long is it going to take to make that pretty picture?
1 second.
Well, no, I mean, it's going to take a long time. Let's say that it takes, let's say that this takes a year.
Oh,
Let's say it takes a year to make one full time around. How long is this going to take to make one pretty picture? So one full cycle?
A year.
It's
A
going to
year.
take a year, which is also known as our trip around what?
Around the sun.
Around the sun, exactly. So if we were to do that, we could actually look at it and see that it takes one full year to make that picture, because that's how fast we're going around. Now, if we were to look at the Earth going around on its axis, that would be one full day.
Yep.
Right? If we were looking at something like an electron flying around the nucleus of an atom, it would be much, much faster. The distance is much, much smaller. And what would happen is that the time would be very short and the frequency would be very high. But, you know, a sine wave is a sine wave. It's just that it just goes faster and slower. Now, the other thing you can change with a sine wave is, notice, what was our peak right up there? How high did we get?
90 degrees.
Well, yeah, but what's our amplitude? How high was this? Remember, we started with a circle of unit 1, so we made it up to 1, right?
2.
So, but what if we instead made this a really big merry-go-round, where we were now at 2 units. Our amplitude of our sine wave would now go all the way up to 2 and all the way down to -2. So basically the size of that merry-go-round, the size of the circle changes how big that sine wave gets. So now if I were to draw this and instead say that we were going to make a circle that was now this big, where our voltage was, or our amplitude, the thing that we were measuring, was 170, then we would get up to 170, and we go down to -170. And that would actually be what the voltage coming out of our wall socket looked like. You know, we call it 120 volts. Does everyone agree with that?
Yeah.
120 volts. Well, it's actually a sine wave with its high spot at +170 and its low spot at -170. So
Why?
because
Why
that's
doesn't it stay at 120?
okay. The reason that it calls at 120 is actually a really good question. And the reason it's called that is that it is something called the RMS value, which is the root mean square. And what the root mean square is the DC power equivalent. And so this is RMS of AC. That's alternating current. AC typically looks like a sine wave. DC is a constant voltage or a voltage only on the top or the bottom of that chart. And we're going to get into that as well. But that's why we call this, darn it, that's why we call this 120 volts, because that's actually 120 volts RMS. In other words, if it were a DC voltage, we would need 120 volts DC to create an equivalent amount of power. And the reason, and the reason that is because we're going to get into this also of Ohm's law, where E is equal to I times R and P is equal to I times E, and power is equal to current times voltage. And what is the value at this point right there at the 180 mark?
0.
0. How about at the 0 mark?
0.
0. How about at the 360 mark?
0.
0. Okay. So if that is a voltage, how much power is being made at that time? If power is equal to current times voltage, and the voltage at that point is 0, how much power is being made?
0.
0. So basically your power is 0 at that point. And obviously, where would it peak? Where would you be making the most power?
At the peak of your sine wave, which is
Right.
1.
Well, it's the positive peak and also the negative peak, it turns out. And at each of these points, the value is different, which is why you basically have to take an average, which is the root mean square, which is an average. You have to average it over time, because what happens is that you actually make lots and then nothing and then lots and nothing, and it changes over time. So if you figure out what it is at all points and then add them all together and divide it by the amount of time, you get an average power. And that's what 120 volts is. Dan, did that answer it? Kinda, okay. But that's why we call it that.
Yeah, I kind of follow.
Okay. All right. So now we're getting into, I'm going to erase our sine wave. And I'm going to make a brand new sine wave.
But wait,
Yes.
did you say that 120 volts is the average because of the way the sine wave moves, but the peaks are at 170 each?
It's actually not the
minus?
average. What it is the equivalent voltage at which, like, let's say this is our time and this is our voltage. Our sine wave would look like this. A DC voltage goes up to a certain voltage and stays there.
Right.
The
Okay.
amount of power, which is actually proportional to the square of the voltage, power is equal to voltage squared, or E, or I'm going to use E. E squared divided by R. In other words, if I were to now take a look at the average power over a unit of time, I would do power average is equal to the integral from 0 to t of P dt divided by integral from 0 to t of t, of 1 dt. Right? Well, this is just integral from 0 to t of E squared over R dt. And it turns out there's a square root term in there, and this is just time. So it's actually a little more complicated mathematically.
Sure.
But it basically comes down to averaging. And it's averaging of power rather than averaging of voltage. Okay.
The test doesn't go that far, does it?
No, it doesn't. However, when you get to the general or the general and extra class exams, it does. So it's good to know anyway. But no, this test does not cover that. Okay, so here's a crudely drawn sine wave. So now we're going to look at this sine wave, and we started with a circle, and we also have this thing called t, which is in seconds, which is the amount of time needed to make one full cycle. That's known as our period. All right. Okay. And what's the definition of frequency again, somebody? What is
How many
frequency?
times per second it takes?
How
to do
many,
one cycle?
how many things per second there are,
Hertz.
right? And it's hertz, and it's frequency, and it's in time, things per second. So if this thing takes t seconds to happen, the frequency is 1 divided by t. So if this were 10 seconds to happen, the frequency would be 1 over 10 hertz. So they're inversely proportional to each other. And now we're going to add something else to this. We're going to add another feature and say that this particle thing, which is tracing out this pattern in space, is now moving at a certain speed. And we're going to say that at first, we're going to say that this thing is now moving at 0 speed. Right? It's 0 speed, 0 meters per second. Right? So it's not moving at all. So what pattern will this thing that's moving through space track out in space?
Line.
Yeah, it'll go up, and then it'll go down, and then it'll go up, and then it'll go down, because how fast is it moving?
Sure.
It's
Zero.
not moving at all.
We don't know yet.
We don't know. Well, it's not moving at all. So it's just going up and down and up and down and up and down. So it's making this just straight up and down line. So now as it's moving, let's give it some speed, shall we? We're going to give it some speed. And we're going to say that now it's moving at a certain speed that's making it do this. Okay, so it's moving at speed. And this is equal to, let's say, 1 meter per second. And we know that this thing is now, it's moving up and down, because we already said that it is, and it's moving at 1 meter per second. Well, okay. And we know that it's going around with a t with a period of 1 second. Okay, so how long does it take to make one full trip up and down?
1 second.
1 second. If it's moving at 1 meter every second, how far is this distance?
1 meter.
1 meter. Well, what's nice about that is that we had a unit of time up here, a period. But what is this? What is 1 meter?
Distance?
It's a physical distance. That's right. So now let's instead say that it's moving at 10 meters per second. How much length would be carved out by that same thing?
10 meters.
10 meters. It's moving 10 times as fast. All right. And we know that the frequency is equal to what? If the time is equal to 1 second, what's the frequency? 1 divided by 1 is 1 hertz. So we now know that something that has a frequency, a thing that's going up and down at a rate of 1 time per second with a frequency of 1 hertz, if it's now moving, a particle that is moving and has a velocity of 10 meters per second will carve out a pattern that's 10 meters long. This is known as a wavelength because that's a wave. Everyone agree with that? That's a wave. This is now how long the wave is. That's called a wavelength.
Now
Okay.
that wavelength of 1 meter is literally about a yard long.
That's correct.
We're talking about an actual,
We're talking about a physical thing.
okay.
That is a really important thing to remember because that's going to have very profound results very, very shortly. So now we're going to say instead that our velocity is equal to 100 meters per second. Okay, what's our new wavelength? How physically long is it? We're still going up and down. That's right. It would be 100 meters, which is how big?
Pretty long.
About 340 feet.
Yeah.
Okay, so now we're going to change it again and say that our velocity is 300 meters a second. Okay, how long would our wavelength be?
300 meters.
300 meters. That's about 1,000 feet. Anybody have a guess as to what 300 meters per second is in terms of your daily life?
Fast.
Speed of sound. Speed of sound. That's about the speed of sound. So that's why if you go to a sporting event, let's say a baseball game, and you see the crack of the bat, you know, you see somebody hit the ball. If you're way out in the bleachers, you can figure out how far you are from home plate by figuring out how long it took that wave to get there. You could also figure out how long the wavelength is by figuring out what the frequency is. And that would actually tell you how much distance is between the peaks and valleys of the wave. All right, so here's our next leap. Okay, so here's our sine wave again. All right, this has a frequency of 1 hertz. Our period is 1 second. So now we're going to say that we have a velocity of 300 million meters per second. Anyone know what that is?
Speed of light?
Speed of light, that's right. Okay, so if we have a velocity of 300 million meters per second, and that's how fast this thing is moving, and it has a period of 1 second, and thus 1 hertz of frequency, how much space is carved out? What is the wavelength of that wave?
300 million meters.
Yep, which is a really big distance, isn't it? Or you could say 300,000 kilometers. Do we have any reference for that? 300,000 kilometers? Well, this is known as the speed of light. Right? That's known as the speed of light. 300,000 kilometers is known as a 1 light second, which is how far light travels in 1 second. Well, it's a pretty big distance, isn't it? This is also about 186,000 miles. That's how far light travels in 1 second. Or if you were to create this pulse of energy and give it a frequency of 1 hertz, 1 full wavelength would be about 7 times around the Earth. Okay, so now the next thing we're going to do is we're going to say, well, okay, we messed with our velocity. We came up with this thing called the speed of light, which is, once again, what's the speed of light? Everyone?
300 million per second.
300 million what?
Meters.
Meters per second. It's a distance, right? Distance divided by a time. That's really, really fast. Okay. And now we know that if we have a frequency of 1 second is our period. Our frequency is 1 hertz. Well, we know that that translates to 300 million meters of wavelength. And for wavelength, we use this little Greek letter lambda. That is the symbol for wavelength.
Can you make another one? Another lambda? Okay.
That's the Greek letter lambda.
All
Little,
right.
little letter lambda, which is wavelength. Okay, so if we have now 1 hertz, a 1 hertz frequency at the speed of light, that translates to 300 million meters. Okay, but now, instead of taking 1 second, let's say that this takes 0.1 seconds. So what would happen to our frequency? If it takes 0.1 seconds to make that wave, what would happen to the frequency?
10 times higher.
Yep, so it would be 10 hertz. Okay, so if it's now, instead of looking like this, it looks like this, what would happen to the wavelength?
Shortens.
And what would it be instead of 300 million meters?
30 million?
30 million. All right, so what have we found here? We found that we have a relationship between frequency and wavelength at a given speed, which in this case is going to be the speed of light. So now let's take this and say that instead we're going to make this 100 hertz. Well, we're going to knock out 30 and that becomes 3 million meters. Okay, so now let's make this 1,000 hertz, adding another 0. We're going to have to knock out some more zeros here. That becomes 300,000 meters. Still pretty long, right? Okay, well, let's add 3 more zeros and make this 1,000,000 hertz. We're going to knock out 3 more zeros. Okay, so anyone know what this million has what that million translates to in our common terminology?
1 megahertz.
That would be 1 megahertz. Mega is the shorthand for 1,000,000. That translates to a wavelength of 300 meters. Okay, where would we find 1 megahertz of light? So light with a frequency of 1 megahertz. Anyone ever turned on the AM radio in the car? There you go.
Yeah.
That's 1 megahertz. Now, your radio probably says something like 1090, right? That's actually kilohertz. And what does kilo mean?
Thousands.
Kilo means thousands. So that's 1090000. Well, I can take this and go 1, 2, 3, 4, 5, 6. That's 1.090. And now there's a mega. So that's 1.090 megahertz. So here we go. We just basically said that our car radio, when it's tuned to 1090 AM, is at 1.090 megahertz, which basically means it's looking at approximately what wavelength of wave?
300 meters.
300 meters. It's looking for a wavelength that's about 300 meters long. If I were to retune this radio somehow to a frequency of 2 megahertz, which is 2 million hertz, let me erase that. Instead of 300 meters, that would now be how long?
600 meters.
Nope. Remember, if the frequency goes up,
150.
150, yeah.
150 meters. So basically, as my frequency goes up, my wavelength goes down and vice versa. So as you see, there's a relationship here. And the relationship is that V, which is the velocity, is equal to frequency times wavelength. This is really important. V is equal to F times lambda, where F is the frequency and lambda is the wavelength. And velocity, for all intents and purposes for what we're doing, is the speed of light. And what's the speed of light? We have another letter for it. That's little letter c. And everyone ever heard E is equal to mc squared?
Yep.
Right? Very famous Einstein equation for rest mass of a particle. Well, there's that speed of light. There's that letter c.
Is that V for a small v for velocity and a big V for volts?
Yeah, and actually to avoid confusion for volts, we're going to use big letter E for
Oh,
electromotive force. So, but we don't need to talk about velocity anymore, actually. For now, we're just going to use our letter C. And until you get to the extra class exam, you don't have to deal with changing velocities at all. So we can write this in a way that is really easy to remember. I usually do it like this. 300 million. I make an F in hertz and lambda in meters. Okay. Now, unfortunately, what number's up there that's kind of a pain in the butt to deal with?
What number?
Yeah, what number do you see there? That's a kind of a pain in the butt to deal with because it's got a lot of zeros.
300 million.
300 million.
All right, so what I'm going to do is take these 6 zeros, and if I have 6 zeros, that translates to a million. What does a million equal to? A million of anything?
Megahertz.
Mega. We represent that with mega. So we're going to basically take these 6 zeros and erase them, but we have to have them show up somewhere else. Well, what's a place that we see where we often deal with a mega?
Frequency.
Yep.
Megahertz.
So we're going to make that megahertz. So this circle right here, if you can make this circle, you can come up with any frequency for any wavelength. You're going to be perfect at translating these things. So here we go. Let's say we're going to have a frequency of 150 megahertz. The way that this thing works is that since you have this circle, you take the thing, this is a frequency, and 300 is a constant, so you never have to change that. Well, we know the frequency. What we don't know is the wavelength in right here. So we're going to put an X across it because we don't know what it is. And then we're going to put a dividing line here. And what do we have? Lambda in meters is equal to, we're just going to look at the divider line, 300 divided by F in megahertz. What do we get, everybody?
2 meters.
2 meters. Okay. Now, what we're going to do is I'm going to go right here and notice what we have. We have a band that's called what?
Meters.
2 meters.
Oh, well, look at that. We have something called the 2 meter band. And what are the frequency limits on this?
144 to 148 megahertz.
Which is pretty darn close to 150, isn't it?
Yeah.
All right. Well, this is actually really important. We don't, in other words, we call it the 2 meter band because it's convenient to do so. It doesn't represent the exact frequency in a lot of cases, but it represents the approximate wavelength. So if we were to actually calculate it for the center and say 146, it would be about 2.05 meters. But for convenience, we call it the 2 meter band. So when you go and look at a radio, you will be on the 2 meter band, and that's how you define that. Okay, now, really importantly, if you're on the 2 meter band, how long is a wave going to be?
2 meters.
2 meters, that's right. Okay, that is it. That is the wavelength. That is a physical wavelength. So how big would that physically be, everyone?
Meters.
Yeah, how many? I mean, if you hold up your hands, if you stretch your hands apart about as far as they can go, that's about it. It's a physical thing.
That's not 2 meters.
Well, it's almost. It's about
That's
6.5
about a
feet.
meter and a half.
Depends on how tall you are,
All right.
whether you have long arms. But if I stretch out my arms all the way, it's probably pretty close to 2 meters. Okay, so now let's say that I wanted to make an antenna to operate on this particular wavelength. And somebody said, you need to make a half wavelength antenna. How long would it be?
1 meter.
It would be 1 meter long. That is a physical thing, isn't it? So what we've now done is we've now taken something that was basically started with this thing going around a circle, right? Carving out a wave in space, defined how fast the circle was spinning, how fast, that which determined how long it took to carve out that picture, and then created something that was moving at the speed of light and actually generated something called a wavelength, which generates a physical thing called a wavelength. And then to actually use it, we could actually build from it and actually build stuff to receive it. So now let me ask this question. What happens if we change our frequency? If we were to build a receiving thing to change it, to listen to try to pick up a different frequency, a different wavelength, what would we have to do with it?
Change the antenna, bro?
Yeah, you'd have to change the antenna. So now what I'm going to bring up is this right here. Okay, does anybody go ahead?
I'm sorry, Scott. Is that why they load the antennas? Because they overload it, so that way they don't have to make like a 50-foot antenna. They can shorten the antenna by adding electric power to it. That's where this comes in.
No,
so that
when you
way,
say adding power to it, or
yes, because one of the portions of the study material is talking about how you can load an antenna, so that way it shortens the actual physical length of the antenna by adding additional electricity.
no, you
So
don't add
let's say-
electricity. You don't add electricity. You add wire.
Yeah, wire.
You physically make the antenna longer by coiling up a bunch of wire. And it doesn't actually radiate, but it makes it believe that it's physically bigger than it is.
Okay.
So, okay, does everybody see this picture on the screen? I hope so.
Yes.
Okay, so what we have is, notice we have a frequency and we have a wavelength. And let's start all the way at the right-hand side. And that says 3000 terahertz. And what is the wavelength right there? Did anyone see the line between the 100 nanometers? That's really, really tiny, right? Okay, so that's the dividing line between ultraviolet and X-rays.
Do
So
we have this picture in your collection of things that you?
I don't know, but I can certainly send it out.
Okay.
So that's the dividing line between X-rays and ultraviolet. Okay, so let's move to the left. As we move to the left, notice what's happening to our frequency. And it's not going down linearly, is it? Every time we hit another tick mark, what happened to the frequency?
Decreasing by a decade.
Everything goes down by a factor of 10. That's right. So basically, because the way that things are set up, this graph would be insanely large off to the right. So we just basically mark factors of 10. Every tick mark is a factor of 10, which means that between 300 and 3000 terahertz, how many terahertz are in there? What's 300 divided by 3000 minus 300?
2700.
2700 terahertz, right? Tera is a trillion. So it's 2700 trillion hertz. That's a very, very big difference. But now let's look between 3 gigahertz, it says GHz, which is 3000 megahertz, and 300 megahertz. What's the difference in there? Again, it's 2700, but the units is now megahertz, which is million. So there's 1,000,000 times more space available on the right-hand side than on that left-hand side one that we just looked at, right? This is actually really important too, because what that means is that because information requires space, it requires bandwidth on this chart, that let's say you were using the internet, right? And you had a bandwidth of 50, let's say 1 megabit per second to do video. Well, all the way on the left-hand side of the chart where the frequencies are very low, that 1 megabit per second would take up most of the chart. Whereas on the right-hand side, because the frequencies are so high and there's actually so much room, that it would take up very little, which is why the frequencies over on the right-hand side are used for high data communications. So all of this whole thing is known as the electromagnetic spectrum. And what's important to note about this is that all the way on the right-hand side where we have X-rays, and then we have UV, and then what do you see right between the UV and the IR? What do you see?
Infrared.
Yeah, between the infrared and ultraviolet. What do you guys see?
Color spectrum.
The whole color spectrum. That's right. Does anyone know the name?
The rainbow.
Yeah, the rainbow. What do we go? Roy G. Biv, right? Red, orange, yellow, green, blue, indigo, violet. So
Yeah.
the question that I have is, why do we see red as red and blue as blue?
Isn't it
Because
the
they
only
operate
it
on different
absorbs-
wavelengths.
They're different wavelengths. And what in particular allows us to see those different wavelengths as different colors?
The frequencies.
And what about it?
Evolutionary adaptation.
That's right. Our eyes are specifically set up to receive different wavelengths and frequencies and register them as different colors. Our eyes are basically electromagnetic receivers that are able to see a wide array of colors, right? Well, why can't we see ultraviolet?
Eyes failed there.
Right. Our eyes aren't built for it. But if you were a bumblebee, you could see ultraviolet. They actually can't. Certain other animals can actually see infrared, right? We can't. We feel it as heat. Now, if we go all the way down to the left, we notice that as the longer and longer wavelengths happen, we get out of the infrared spectrum, and then at some point it turns into microwaves. Microwaves then go further, and we get longer and longer wavelengths, and then we notice we have these things called HF, VHF, and UHF. Those, basically everything to the left is known as radio. HF, anyone have a guess what HF stands for?
High frequency.
Okay, now the question is, if you look at this whole spectrum, is HF very high?
No.
No, it's not high at all. But it seemed really high back then when they discovered it, and they had really never made the connection between all these different frequencies. So HF is high frequency. And what's the frequency range of HF?
3 megahertz.
3
and 30
megahertz and 30 megahertz.
Okay, this is one of those things that will likely be on your exam and you will be using frequently. Okay, VHF
Very high frequency.
Very high frequency.
And the range on VHF is 30 to 300 megahertz. And then UHF,
Ultra high
Ultra high
frequency.
frequency.
right, 300 to 3000. But since we don't like to use 3000, we made it 3 and we changed from mega to giga. A giga is 1,000 times bigger than a mega. So now the big question is, what is on the HF portion? How much room is there in that area where it's labeled with the letter D? How much physical space is there in megahertz?
27 megahertz.
27 megahertz. How about in the area with the letter I?
270.
270. How about it where the letter O is?
Oh,
Oh crap, it's just like that circle you just showed us.
Yeah. Yeah, but how much, what's the spectrum space between 300 and 3000?
2700.
2700. Okay, if I have a high frequency signal that takes up 10 megahertz of space, where should I put it if I have a choice?
The higher frequency range.
The higher frequencies you go, the more space there is to put it. So if I want to have a very high data rate on my cell phone, what frequency range am I going to operate at?
Probably in the megahertz or gigahertz.
All the way up in the gigahertz range.
you
Because
say
there's a
that
lot.
question one more time. If you
Yeah,
have what?
so let's say that I want to do streaming video, which takes up 10 megabits per second. It takes up 10 megahertz of space. If I were to make that, if I were to choose where to put that, and if I were to redraw that whole spectrum in a linear fashion, where this is 3 and this is 30 and this is 300 and way out to the right is 3000. And the thing that I'm trying to do is physically this wide. Where would I want to put it so it didn't take up much room for everybody and didn't wipe out a whole big chunk of the space? I'd put it way over there where there's a lot more room to put it. And as it turns out, what do we know about the wavelengths as you go to the right as well? As the frequency gets higher, what happens to the wavelengths?
Get shorter.
Shorter, that's right. And if I'm building an antenna, if those are physical lengths of things, what happens to my antennas?
Get shorter.
They get smaller, that's right. Which is easier to build, something big or something small?
Well,
Something small.
So
That is why our cell phones operate in the 1 to 2 gigahertz range, because the antennas are small and there's a lot of bandwidth up there that you can do. That also makes those frequencies very, very, very much coveted for those types of technologies. That's why
5G.
That's why there's something called 5G. That's exactly right. Goes higher and higher frequencies so you can have higher and higher bandwidths. Okay, now that your minds are blown, how about a 5-minute break?
hmm.
I'm okay with that.
Okay, back in 5 minutes. Think about some questions.
Mhm.
You still muted.
I think we're able to communicate still, but I think that's really neat. I never connected those two dots. I've been going over the study material and I've been trying to memorize the questions, but I've been having gaps of information. So, you know, I get A, I get D, I get E, but I don't know the in between. And that's really smart.
There was a lot in that last little bit though that's around the test. So breaking that down and being able to separate it out and memorize the pieces.
Yeah, because I've been memorizing the test and it says, you know, when the bandwidth increases, you know, the length shortens and stuff like that. I know the answer to the test. I just didn't know why. And he just explained the why.
Yeah,
So
that's what most of his classes is, the why behind the questions. So you can try to reason through the questions in a logical manner.
So has anybody else in here been taking the pretest? I recommended the app because I did the Android app and it circles through the 424 questions, I think it is. And as it rotates a certain amount of time, so you start taking, it starts saying that you mastered a certain amount of questions, because as it rotates those questions, if you always get it right, I guess it does a percentage. And I've been doing it for a couple days now, and it's like at 40 something percent. So
Which
now it's
app-
throwing out.
Which app is that?
On the study guide here, I'll show you this one. Make sure you get the right one because it's called the Ham Test Prep. I don't know if you can see it.
I looked at a bunch of them. Oh, the ham test prep.
Yes,
Mhm.
I accidentally downloaded the older test, which goes up to 2018, but there's a
Okay.
new one. There's a new updated one, and it was really neat because as you go over the questions, it and you answer them. If it's wrong, it tells you what the right answer is. So it's kind of like it's a really good study guide.
Can you show the icon again on your phone, what it looks like?
Yeah.
I was using that about 2 years ago. It's a pretty good app. I haven't used it in a while, but I was using that.
I want to just make sure I have the right one.
I
You
don't
might
know
have
if you
to.
can see it. Yeah.
Does it have a with a antenna signal on top?
No, it looks like a diamond with an antenna in the middle. Yeah, it
Oh,
looks like
okay.
a yellow diamond.
Which one's
I
it
got
called?
it.
Which one is
Hey.
it?
It's the one I've been using is the Ham Test Prep.
Okay.
And
There's a couple good ones. There's hamstudy.org.
is that by Inversoft?
Give me 2 seconds and I'll be able to tell you, brother.
Here, this is another one. This one's free as well.
Yes, I've been doing. The reason why I like the app is
Mhm.
because it rotates the questions and it gives you a percentage of mastery. So as it rotates the questions and it's like the questions you always get right, your
Mhm.
percentage goes up of how many questions you've mastered. And I've taken like 30 of the handheld tests, and I started like getting 60s. And then now I'm getting averages of like 80, 85 per test, which is passing. And then the ones I keep getting wrong are the new questions or something I may have forgotten, like I didn't read all the questions. And it really makes me. That's why I was laughing when you were talking about the proctors, because I'm an audio visual learner, so I have to read my material aloud.
Mhm.
So when I take the test, I'm gonna be reading it aloud, and I'm gonna have to have like 6 cameras, so the proctors don't think I'm cheating or getting like a cue.
That's
So
how I study
Here,
too.
so here's another one. This is the ham radio exam ham radio exam tech, which is by this guy named Roy Watson. And it actually, I really like this one because it allows you to take section quizzes, one small section at a time.
Well, if any of you get those ability to put them in the link, feel free to drop them. I'm going to try to drop a couple.
It's called ham radio exam tech. By Roy Watson. And that's free on virtually every platform that I've seen.
And again, how do I play back this recorded session? How easy is that to do?
It's going to be. I'm gonna have it. I'm basically recording it, and I'll put it up on my YouTube channel.
And what's your YouTube channel then?
Yep.
What is your YouTube channel then?
Well, I'll send you the link for it.
Okay.
I don't publish it or anything.
Okay,
So,
that's great.
Yeah.
Thanks.
Protects everybody's likeness, you know. So, all right. Any questions before we move on? No? Okay. Well, we're going to diverge a little bit from the way it's laid out in the book. And the reason we do that is because I think that what's really important to cover now that we understand frequencies and wavelengths and stuff is we go to page number 24 in the book. And page 24 is radio wave characteristics. So we now know, we're going to be on page 24, that radio waves are really no different from light waves, which are no different from X-rays, which are no different from any other electromagnetic wave. All right, so what makes them all the same? They're all what kind of wave?
A sine wave.
And well, actually, they don't have to be sine waves. But what kind of wave are they? They are electromagnetic. Right? And what are the two parts of an electromagnetic wave?
Electric and magnetic.
Electric and magnetic. Okay, very good. So if we were to draw an electromagnetic wave as it's traveling through space, what we would see is this. We would have an electric wave like this, and a magnetic portion of it that would look like this. If we had a 3D plot, and the motion of direction, it would be going in this way, in this direction. So we have our electric wave or electric energy, and we have our magnetic field, which is an H or a B. We can use either one for that. And the direction of motion, this is actually known as the pointing vector, or P-O-Y-N-T-I-N-G. P-O-Y-N-T-I-N-G, named after a guy named Pointing. It's not actually pointing in a particular direction, although it happens to be. Okay, now, one thing that's very important to note is that, again, electromagnetic energy, as it travels through space, has an electric portion and a magnetic portion. So everybody hold up your right hand. It has to be your right hand, not your left hand. Stick out your thumb, stick out your index finger, and now stick your middle finger straight out so that all three fingers are perpendicular to each other. Right? This is known as the right hand rule. So E cross H, this is your electric field, your magnetic field, and this is direction of motion. So basically, if you have an electric field and a magnetic field, this is the direction, the way your middle finger points, that the energy is going. So E cross H is S. So that's just really important, but if you, it's not, you don't need it for this test, but if you ever start to wonder what the right-hand rule is, this is the right-hand rule, and it's used for defining the direction of travel and direction of energy flow.
Okay, just say again, what's the thumb doing?
The thumb is your electric field.
And the middle finger is?
Your index finger is the magnetic field.
Okay.
And then the S is with the direction of motion of the wave.
Okay, your middle finger then is the direction of the motion.
That's right. So you will see if you have something going the direction of your middle finger, you'll have this one, and they'll always be perpendicular to each other. Okay, so what that also means is that, notice they also get to the 0 point at the same time. Oops. Right, they all go through this, darn it, stop it. They all go through zero, they go through zeros at the same point. They're always perpendicular to each other. Okay. How fast does a radio wave travel through free space?
Speed of light.
300
Speed of
million
light.
meters per second.
That's right, 300 million meters per second, which is the speed of light. The distance that a radio wave travels when it makes one full sine wave, what is that known as?
Wavelength.
A wavelength. Okay, excellent. All right, so the formula for converting frequency to wavelength, we can draw that circle. 300.
300 divided by
and
f is equal to wavelength.
Yep. Or we could write this out as 300 equals F in megahertz times lambda in meters. And they're the same thing. So, okay, as the frequency goes up, what happens to the wavelength?
Goes down.
Okay, as the wavelength goes up, what happens to as the wavelength gets longer, what happens to the frequency?
Goes lower.
That's right. Okay. So let's say that I made an antenna and I have an antenna tester, which I do have, and So I found out that my antenna is supposed to have a dip at, let's say, 147 megahertz. And I find that the dip in on my meter comes out at 142. Does that mean my antenna is too long or too short?
Is it too long?
It's too long, because just like if you think about it, if you have let's say a musical instrument, let's say let's say a pipe organ. What happens if the pipe is too long? What happens if the pipe is made longer? What happens to your frequency?
Goes lower.
It goes lower. Things that are bigger have lower resonant frequencies. So if I wanted this and I ended up with this, that means that my frequency is too low. Therefore, my antenna is now too big. So what do I do with it?
Shorten it.
I shorten it. That's right. So why is it better to have something that starts too low a frequency?
You can fix it.
You can fix it. That's right. What happens if the frequency is too high?
Then you got to redo the whole thing.
You got to redo the whole thing because you already cut it too short. That's right.
Get another antenna.
Yep. You start all over. Okay. What frequency range is high frequency, or HF?
3 to 30.
Back on the screen. That would be 3 to 30. And VHF is
30 to 300.
Yep. And UHF is
300 to 3 gigahertz.
300 to 3000 megahertz or 3 gigahertz. They're the same thing. And the term RF stands for radio frequency. All those things that are in radio are known as RF, or radio frequency. Okay, so now we are moving on to the next section. And we are going to cover propagation. So the first thing that we have to do is draw this big glowing thing in the sky. Anyone know what that big glowing thing in the sky would be?
Sun.
That would be the sun. Okay. And now we're going to draw this thing where we live. Not drawn to scale, obviously. And what would this be known as?
Earth.
That would be Earth. Okay. So we are lucky because what surrounds the Earth?
The atmosphere.
We have an atmosphere. That's right. Okay. If we didn't have an atmosphere, what would happen to all of the energy that the sun was emitting?
It would just float away.
Boil us alive.
Yeah, it would basically, we would
cook.
We would cook. Basically, there would be nothing on the surface of the Earth. It would be completely eliminated. There would be no life. There would be the word is that the planet would be sterilized. There would be nothing here. So instead, well, let me ask, what does the sun put out as far as energy goes? What wavelengths?
Are they electromagnetic?
They're all, yep, they're electromagnetic. What are what types of electromagnetic light energy are we talking about?
X-rays.
X-rays. What else?
All waves, right?
Yep, UV. Yeah, anyone ever gotten a sunburn? That's our sun. That's our skin's reaction to ultraviolet. Other wavelengths?
Gamma rays.
There's gamma rays. Other ones?
Visible spectrum, IR.
Yep. Light, infrared. How about other ones?
We have microwaves.
Microwaves. How about other ones?
Sounds like you're saying full spectrum.
Yeah, there's also, the sun is also a very big radio frequency emitter. Okay, so basically the sun puts out everything, right? It makes energy at lots and lots and lots of different wavelengths. Well, this poses a problem, doesn't it? Because we have all these different things that we want to listen to and we want to use. And we also don't want to be cooked. So we're actually surrounded by this atmosphere, also not drawn to scale. All right. So here's our
Radiation belts
atmosphere.
as well.
Hmm?
The Van Allen radiation belts diverting some of this.
They do, yeah. But that's usually in a part. Those are usually particles. That's usually particulates, charged particles. Okay, so now we have this thing called the ionosphere. So where do we live? What level? What is the area where we live?
Troposphere?
That is the troposphere. That is the troposphere. Okay, and above that, we call that the stratosphere. Okay, that's where we fly jets. The air is getting thinner up there. And above the stratosphere,
Mesosphere?
yeah, I believe it's the mesosphere. And how about above that? And we're getting into the cool stuff.
Ionosphere?
The ionosphere. And this starts about 30 miles up. And it goes out to about 600 miles. Okay, so the ionosphere, what do we know about the atmosphere the higher you go?
Thinner.
It's thick at the bottom and really thin at the top, right? And in fact, it's so thin that a lot of your satellites are orbiting at about 200 miles up. They are technically in the atmosphere. They are actually experiencing drag caused by the atmosphere. So that's why they have course corrections. That's why things that are put up in space will eventually, if they're in this low Earth orbit atmosphere, will eventually come down because they're being slowed down continuously. They're actually inside the atmosphere. But it's really thin. So what we know about our ionosphere is that the air up there is pretty thin, right? Humans can't survive up there. So, but what we also know about the ionosphere is that it's made of air, right? Okay, so what are our main components of air?
Nitrogen, carbon, oxygen, a whole bunch of gases.
Nitrogen, oxygen, some CO2, some well, I meant a little bit of methane, but I actually meant NH3, some argon, a few other things, but nitrogen and oxygen are 99% of it, right? The other stuff, that's basically trace. So for all intents and purposes, we can get rid of those other things. So we can say that it's mostly nitrogen and oxygen. Well, okay, what do we know about visible light? Where does most of it get? Where does a lot of it get to? So a lot of the visible light keeps us bright during the day. So most of the visible light makes it through. A lot of the radio frequency energy, it gets through, but we don't really care.
But wouldn't it cause interference with the frequencies that we are using?
It can, but the same frequencies that we would be using, we actually make more of it.
Ah, okay.
We make more of what?
We make more coherent energy. I mean, now if you were to listen to the radio, you would actually hear noise, right? If you heard static, that's basically the sound of the cosmos. That's the sound of space being made on radio frequencies. But the energy that we emit is coherent. It's concentrated as opposed to all frequencies. Some of that radio frequency energy hits the ionosphere and bounces back out into space. So what happens to the ultraviolet and the X-rays?
Well, they seem to get through because they're damaging.
Well, yeah, some of it,
mediates
but
them.
most of it actually doesn't,
Most of it.
fortunately.
It's heavily mediated.
Yeah, fortunately, most of it doesn't make it down. And depending on the wavelength, so we have higher frequency translates to energy. The more energetic something is, the higher the frequency it will have, and vice versa. So that means that X-rays are really energetic. Ultraviolet, looking at that chart, a little less energetic. Well, what that also means is that when those things come out of the sun, when that electromagnetic electromagnetic energy comes flying out of the sun and it gets to the atmosphere, depending on what it is and depending on how dense the atmosphere is as far as things floating around in it. Remember, it's a lot denser down here than it is up here. And that changes over different altitudes. There's that basically turns into a probability of any particular photon coming out of the sun striking an atom. And if it happens to hit it just right, it transfers its energy to that atom, which was stable, and it knocks an electron off of the atom and turns it into a free electron. And let's say this becomes a nitrogen with now a positive charge. So we have an electron floating around and a nitrogen molecule with a positive charge floating around. So what do we know about pluses and minuses when they meet?
You're going to get lightning.
Well, but what happens to them?
They attract each other.
They attract each other. Right. So in theory, this would happen and they would immediately go back together, right? Except that they're now kind of a far distance apart. The higher up you go, the density of the atmosphere gets thinner and thinner. So the chance of them actually meeting goes down. Well, the chance of them being made also goes down because there's less stuff to make. But what that basically means is when the sun is shining, you have a continuous generation of electrons and ions, and then sometimes they meet and they join back up, and then they disappear and they just turn back into nitrogen again. So you basically have this situation where you have a continual generation and evaporation of electrons and ions up in the atmosphere. Well, okay, so there's another name for a lot of electrons floating around in a space. Does anyone know what that is? It has a name. It's the fourth state of matter. Has anyone heard of something called plasma?
Yeah. Oh, yes.
Okay.
Yes.
So basically, the sun causes a plasma to form in the Earth's atmosphere. And depending on where it is and what made it, that will determine how thick the plasma is. And it will determine when it gets made and how fast it goes away. Because different wavelengths, different energies of particles coming out of the sun, different photons, will penetrate to different depths of the atmosphere. So what you end up with is you end up with distinct bands that form in the atmosphere. You start with the bottom layer, which is known as the D layer. And then above that, you have the E layer. Anyone have a guess as to the one above it?
F.
That would be F, yeah. And in fact, the F is actually F2 and F1. Turned out they found that there was actually an F1 layer. Well, it was assumed that there might be something below, so they left ABC space for it, but they've never found it. So these different levels of the atmosphere, the ionosphere, do very different things. So when do you think ionization would be at its peak? Considering that sunlight makes, sun's energy makes these ions form. And at night, when there's no more sunlight, what happens if you find just a random electron meeting up with an N2 plus at night, and there are virtually no additional ones being made? What would happen with those rejoin? They would disappear. So what do you think? Do you think you would have higher levels of plasma during the day or at night?
Day.
Daytime, exactly. So what you end up with is this, it's called a diurnal cycle, basically day and night, where you have high levels of ionization forming during the day, and then it dissipates at night. And in fact, what ends up happening is that we can actually hear this on the radio. This is evidenced by the fact that if you've ever listened to AM radio during the day, you hear very local stations only. At night, you hear some local stations, but you hear very distant stations as well. The reason that happens is because during the day, you have this D layer, which is at very low altitudes, which forms and it's very thick. And what it serves to do is this becomes absorbing below 10 megahertz. And where did we say that AM radio was? How many megahertz?
1.
1 megahertz. Well, guess what? Your AM radio signals go up into the atmosphere, and what happens to them?
They get absorbed.
They get absorbed, and it never comes back down, which means that the only if this is your AM transmitter down here, your AM radio transmitter, it can only be heard in this range on the ground, because anything that goes up toward the sky just goes away. It gets absorbed by the atmosphere and never comes back. Okay. The E layer is typically reflective at a few different frequencies, but we usually ignore it because it doesn't do a whole lot for us. The king of all of this is the F layer, and this has something called a maximum usable frequency. And what this does is that signals that get up into the plasma up here in the F layer, if they can make it there, they get here, and this actually changes the index of refraction, and it takes the light or radio waves and can bend it, and guess where it ends up? Where is that?
Far away.
Yes, reflected
Far away,
backward.
that's right. And this can actually be 2,500 miles away. That can actually be coast to coast. So let's ask this question. Because
That's the F1 and F2 layer that would do that.
Yep.
And what
And
does MUF stand for again?
maximum usable frequency. And so the maximum usable frequency is proportional to the amount of ionization that has occurred. So basically the thickness of the plasma. So now,
Can you say that again with that last thing?
yeah, basically the thickness of the plasma that has formed, the density of the plasma determines what the maximum usable frequency is at those frequencies. So during the day, because you have more plasma, your maximum usable frequency will typically go up. At night, when it starts to fade, your maximum usable frequency will typically go down.
Hey, Scott,
Yeah,
if you're going 2,500 miles away, then you might have day at different times for those
Exactly.
two different locations. But
That's
how does
exactly
that
right.
impact things?
that's exactly right. When you say 2 different times, are you talking about timekeeping
I'm
or?
I'm talking about daylight, right?
Yes.
So if
Yes.
you're saying day impacts this, you could have daylight 2,500 miles away at a very different time.
That is very true. And in fact, now that you mention it, what I'm going to bring up is a picture of that. We're going to look at the, let's find something on the day-night Terminator, call sign grid square JO65. Let's see what that looks like. Okay, I'm going to bring up a map. Hopefully. I hope. Why this is arguing with me today. Let's see, CN84. Really? You're going to be like that? Okay. It's going to be like that. I wonder if they're down. All right. I was looking for a map application. So basically what you've got is, as you were saying.
Scott, I got a question.
Yeah.
I got lost for a second there. I thought at night the plasma density would be less and therefore get a better MUF, maximum usable frequency.
It would not be less. Well, the question is.
I thought it would be more maximum usable frequency at night because of the plasma thinning and less energization.
No, the more plasma you have, the higher the MUF.
Oh, okay, I'm sorry, I got that wrong. Thank you.
In those higher frequency ranges, or because wouldn't for AM radio, wouldn't it stop being absorbed?
That's a very good point. So what ends up happening at night is that your D layer, because it dissipates very, very quickly, all of a sudden your AM radio frequencies, and then the maximum usable frequency comes down. Actually, it turns out that AM radio at 1 megahertz is actually a very low frequency, right? Well, it turns out that now the D layer goes away. There's essentially nothing left there because the density of the air density is much higher. That D layer goes away pretty quickly, and then your AM radio signals at 1 megahertz, because the MUF goes down as well, all of a sudden can be refracted over long distances, and you can have AM radio that then covers 2,500 miles, which is actually what we hear at night. Our AM radio band, from just listening in your car, you can receive very long distances. So what I wanted to bring up was, yes, I'm going to get rid of that picture. And this is something called PSK Reporter. And so to answer your question, what happens on this day-night terminator? Well, if it's light here and dark here, we actually call this the gray line. And on that line, where you notice that if you went all the way around the Earth, you would see that it goes all the way up to the poles, right? And depending on the season that you're in, we happen to be right at the equinox right now. So we get light at both poles, but in the summertime, the North Pole is completely lit up all the time. And in the wintertime, the South Pole is completely lit up all the time in our wintertime, which basically means that our propagation changes drastically from summer to winter over long distances. And yeah, we do see that. And it is quite drastic. What that also means is that if you have somebody who's on the daytime side and somebody who's on the nighttime side, that means that it's that depending on where your signal gets to when it makes that first skip in the sky, when it first hits the atmosphere, that can determine what it looks like. So even though you would think, for instance, that a very high frequency, as soon as night fell, let me draw the picture here again. So let's say that this is the Earth, and so here's night, and here's me, and so this would be our, let's see, this would be our evening, and here's Europe way over here. You would think that this path would probably be an unusable path because most of it went through the night, but because the sunset is basically moving this way, these areas in here recently received sunlight. So this, for instance, that skip, and that skip, there might still be enough residual ionization left for that to work. Similarly, if we were to look at it in the morning, in our morning, and so, sorry, at nighttime. So, no, let me get that right. Let me get it right. In our morning, so looking at, for instance, Japan, nighttime in Japan, and morning over here where we live, and so here's Japan. Well, it's morning, but the as the sun coming up is moving in this direction, we haven't really gotten a lot of ionizing radiation yet. So we will lag behind for a couple of hours. And right after sunrise, we might have some very, very good, very low frequency propagation into Japan or into Indonesia or Australia. So yeah, right where the day and night change over, you get some really interesting stuff happening. I know, for instance, on one of the bands that usually you would think of as dead, not being able to carry any signals, at 8 o'clock last night, one of our guys here in the club was talking to Lebanon. So, and you look at it and it should never work, but it was working. And you can't argue with the fact that something is working. You just go ahead and use it. So.
An AM question again.
Yeah.
So the AM frequencies in the daytime get up to the D level and they're absorbed. They don't function very well, but at night, right, that D level dissipates and then they can fling themselves way up into the F where they get bounced back.
That's exactly right.
Thank you.
Yeah. And that's why if you listen from your car as you're driving around in the middle of the night, you can hear AM radio signals from 1,000 miles away.
Yeah.
Whereas during the day, you heard absolutely nothing. Okay, so that's HF propagation. And now what we're going to do is look at this. I'm going to share this band plan. Okay, so now we're looking at page 31. And so our frequency spectrum is really split into, notice we have VHF, UHF in frequencies and wavelengths, and then MF, which is medium frequency, which is like way down here, and the high frequency bands. So there is, if you want to think of it this way, there is like a dividing line right about here at the 20-meter band. And below this, you would consider these bands to be night bands. And up here, you would consider these to be day bands. And that is because of ionization levels and the fact that the Earth is spinning and sometimes it's day and sometimes it's night. So these really low frequencies, those become the night bands, and the upper frequencies become the day bands. And notice, where do we have that transition?
20 meters.
20 meters. Okay, so has anyone here ever been on 20 meters before? Just out of curiosity, if you have some experience. 20 meters is the long haul, always okay band, because it's kind of in the middle. If it's a particular, during the winter time, maybe 20 meters dies off at night. During the summertime, sometimes it stays alive all night long. You can't really tell. But by and large, anything that is a nighttime band will be pretty much dead during the daytime, and vice versa. And when I say dead, that basically just means that the propagation doesn't support communications. So page 31, what part of the atmosphere enables the propagation of radio signals around the world? What's that called? Starts with the letter I. That's called the ionosphere. Yeah, and we're just going to ask questions and you guys answer them. Okay. Which of the following is an advantage of HF versus VHF and higher frequencies? What do we get on the high frequency bands?
Like more bandwidth.
We get long. Oh no, we get long skip. We can cover very long distances. So the high frequency bands, they can cover very long distances by skipping off the atmosphere.
Oh yeah, I'll get it. Okay.
Okay, so now we're going to pull this chart up again. And okay, notice that we also have this thing called the 6-meter band. And the 6-meter band is at 50 megahertz and therefore is part of the VHF band, correct? Okay, so the 6-meter band is part of the VHF band. Now, do you think it would take more or less ionization for that kind of propagation to exist on the 6-meter band? What does your gut say? The higher the frequency you go,
Smaller your antenna.
right? But what about ionization? What about levels of ionization up in the sky? The higher the frequency you go,
Less ionization. Oh,
I
no,
hope
the more.
the more ionization you need. That's right. So this would be
The
if
more you need or the more you meet? What did you say?
the more you need.
Okay.
Basically, the higher the frequency you want to operate on, for if you're bouncing signals off the ionosphere, the more ionization you need, which basically means that the sun has to be doing more work for you, right? Okay, so the sun, in addition to moving around in our sky or appearing to moving around in our sky, also goes through 11-year cycles where we have sunspot numbers that go like this. This is 11 years. This would be 22 years. This would be 33 years. And what this does is when the sunspot number goes up, the average amount of ionizing radiation, which creates ions up in the atmosphere, goes up. So what we end up with is this thing called a peak. And this is a peak. And this would be the bottom. And this would be the bottom. And unfortunately, we are actually right about here right now. We've spent a long time in the bottom on this cycle. These cycles started being numbered in about the year 1670 or so. So maybe it was a little later. But this, we are now in something called cycle 25. So about 1700. So we are now in cycle 25, and it started way down here, and we're just on the upswing, which basically means that the number of sunspots that we see on the face of the sun, which translates approximately to the amount of ionizing radiation coming out of the sun, is going up. When we're at the top, what we might see is that the 6 meter band and the 10 meter band are open all day and all night because there was so much ionization made during the day that there was a lot of it left over for nighttime. So we might have like worldwide propagation on those bands. At the very bottom, we would be lucky if we get 17 meters and the 15 meter band open during the day, just because there's very little ionization occurring because the sun is not particularly active.
Scott,
So,
I thought you
yep.
said that when the sun splits the molecules in the atmosphere apart, and you've got the electrons and the positive ions, the nitrogen ions, that you get more of those during the day, and that those block signals.
Well, it depends where they occur. So here's the D, and here's the E, and here's the F, F1, F2. Right? If they build down here, this blocks at less than 10 megahertz. That is exclusively daytime on the D layer. The F layer up here, this is a refractive layer that when stuff gets up into it, up until the point that it just basically goes off into space, it gets bounced back down. So we're kind of having them compete against each other, which is why this is so interesting and why it's kind of hard to predict. Kelly, does that make sense?
At nighttime, we're going to have greater ionization in the F levels, and that's why we're getting better propagation.
Well, at nighttime, everything is dissipating, but the D layer dissipates faster.
That's why at nighttime you can get further and further distances because the D layer is not getting in the way, correct?
Well, at lower frequencies, yes. Now, let's say that we were to pick a frequency of 21 megahertz. What would happen during the day, as an example?
And it can cut through the D layer.
It goes right through the D layer. And if the MUF, let's say the MUF is 27 megahertz, that would be the maximum usable frequency. So what would happen to that 21? It would get refracted back down. So now let's pick a different one. Let's pick.
How do you know it's going to be 27 megahertz up in the F1, F2? Or did you just pull that number?
Ever heard of something called space weather?
Yes.
Yes, that is a prediction caused by space weather.
Okay.
So
you can virtually look that up.
Yep.
Ahead of time.
But I mean, it's based on observations.
Okay.
And there's actually something called the NOAA SWPC, which is the Space Weather Prediction Center. Space weather is actually really important because all those satellites up there are exposed to space weather. Space weather is what the sun is doing. So it's actually really important. All right, so now what we're going to do is we're going to pick another frequency, and we're going to pick, let's say 3.75 megahertz during the day. What's going to happen to that?
It's not going to get to the D layer.
That's right. It's going to shoot up to this D layer, and it's just going to heat up the sky. Basically, it'll transfer all its energy, and it'll never come down. You'll never see it again. Okay, so now let's take this and let's go to 222 megahertz, which is another ham band. What happens when 222 megahertz gets up to the D layer? Passes on through. What happens when it gets up to the F layer, where the maximum usable frequency is 27 megahertz, and we're on 222? What would happen to it?
Open space.
You're talking about ISS at that point?
Goes off into space. That's how we talk to satellites. That's how hopefully we can talk to aliens, because those signals will just shoot off into space. If we have a satellite that's out here, that's how we talk to our satellites. We use VHF and we use UHF to talk to satellites because they just pass right through the atmosphere like it's not even there.
I thought you said satellites were still in the ionosphere.
Depends. If we're looking at a low Earth orbit, such as the ISS, those are about 220 miles up or so. That's somewhere up around here. If we're talking about geosynchronous satellites, a lot of communication satellites that are in a fixed position, those are at 22,000 miles up. And the reason that we do 200 miles up versus 22,000 miles up, and the reason we would do that is because these low satellites cost a lot less money to put up than the high ones.
It's latency too, isn't it?
What?
It's latency too, isn't it?
Well, yeah, it is. I mean, 22,000 miles, that actually takes a little bit of time to get that signal up there at the speed of light. So if you're using a communication satellite, there's actually a little bit of a delay.
What about Starlink?
Starlink is, I believe, a low Earth orbit, but there are a lot of them. So, but actually, if you were to, for instance, let's say we look at, I'm going to share this. Let's say we were to look at Amsat Iss Predictor. Okay. So here's the International Space Station CN84LA. Calculate position and predict. Okay, so let's see where it is. So this is the International Space Station. That makes one complete orbit of the Earth every 90 minutes. Now, if you go through and do the math for that, you'll find that one complete orbit every 90 minutes is a speed of about 17,000 miles an hour, which means that if we're looking at the Pacific Northwest, for instance, to go from, because it's only 200 miles up, to go from being visible to being invisible as it makes one pass is about 10 minutes. And we'll find that if you look at this right here, you will see this acquisition of signal on a good pass. Let's look at a high altitude pass. So it occurs at 818 and disappears at 829. which basically means that a low Earth orbit satellite is in view for, as we see, 10 minutes and 52 seconds. So which do you think it's easier to talk through? A satellite that isn't moving with regard to you, it's just directly overhead, or one that's flying across the sky that you have to keep moving your antennas? That's why Starlink, because it's a low Earth orbit, requires thousands of satellites that then communicate with each other, because they're all moving around all the time.
Quickly going in and out of comms.
You're constantly picking up and losing satellites. Whereas a geostationary or geosynchronous satellite is at a high enough altitude, like for instance, your direct TV signal, if you have satellite television, or like, I want to say like Hughes cable, which uses a satellite.
GPS?
GPS satellites actually do move.
Okay.
They actually do move with respect to the Earth. But like a geosynchronous satellite will actually stay at the same location. They have basically a parking spot up there, directly overhead of something.
You mean
we actually get into satellites too here? Yeah.
It's designed to stay above us, right where it always is.
Yep.
As if it's attached by a balloon.
Yep.
It's basically falling around the Earth at the exact same speed the Earth is rotating.
Yep. So that it appears to be just directly overhead all the time, directly overhead. Okay, let's see. Which of the following bands can provide long distance communications during the peak of the sunspot cycle? That would be 6 and 10 meters. So if we're looking at long distance propagation on the 10-meter band, 10 meters was open yesterday to Hawaii till about 7 p.m. It was open to Australia till about 7 p.m. as well. So after dark, but still looking into the sunlight. So dawn to shortly after sunset during periods of high sunspot activity. It's good to have the sunspots back. HF signal propagation can fade. So now what we're going to look at is we're going to draw that picture of the ionosphere again. And we're going to look at this. So here's us. Think of this as a mirror, but it's a bumpy mirror. So we're looking at now a place down here and a place over here. And a signal is sent up into space, and it goes up like this, and it bends and comes back down. But let's say that because it's a bumpy mirror, there's also another path that it could take, which goes like this and comes down at a slightly different angle and ends up in the same place. So because this is, let's say 500 miles up, and this is a bumpy surface, will those two waves get there at the same time? Can you guarantee that?
No.
No. Okay. So now let us draw what those waves look like coming in. You have the first one coming in, which looks like this. And what is that picture again?
Sine.
That's a sine wave. All right. And that has a wavelength that we can draw like this. Well, and how fast is that? How fast is that wave moving toward us?
Speed
of light.
Yeah.
Right. Okay. So now let us take another wave that took a different path up off of those clouds. And it arrives and looks like this. It has the same frequency because it was made at the same time, but it arrived a little bit later or a little bit earlier. And the wavelength is exactly the same, but its timing is off and its amplitude is off. And they're continually changing. Well, if this is completely opposite and equal, and they look like this, what would happen if you add those two things together?
They cancel each other out.
They cancel completely. That's right. Now, they could also get there at exactly the same time, right? You can't predict that. But what would happen if they got there at exactly the same time?
Add up.
They would add together. Now, what would happen if sometimes they added together and sometimes they canceled each other out?
Maybe it's just broken.
Yeah.
You would have spotty connection.
You'd have a spotty connection. And we hear this all the time when you're on the high frequency bands because the atmosphere is not smooth. And this happens constantly. And what you end up hearing is you'll be listening to somebody or talking to somebody. And they'll start to come back and you'll hear them come back again. And that's known as fading. And that's caused by different, that's caused by two different signals or multiple signals taking different paths to get to the same point. And sometimes they add and sometimes they subtract. And if you happen to be in physics, you see this all the time, actually, in the real world. Has anybody ever looked at a puddle with a sheen of oil on it in the sunlight? What do you see?
Diffraction.
The oil.
You see diffraction. You see a rainbow, right?
Yeah.
Well, why? You ever stop and say, wow, why is that happening? And that's actually happening because the oil is causing a layer. The oil is basically causing a layer to form on top of the water that takes waves and does this with them. Some of them go to the bottom and some of them bounce off the top. And when they get to your eye, certain wavelengths have gone a certain distance where they've canceled each other, and certain wavelengths have gone a certain distance where that extra added distance has actually caused them to be additive. So you actually see different colors enhanced and different colors not. And you end up seeing a rainbow. Okay, so now we're going to talk about something called polarization. And polarization is if we have a piece of wire, polarization is the direction of the electric field and it will be parallel to the wire. So I can set up a wire that goes up and down, and that will have an electric field that goes up and down. I can set up a wire that is parallel to the ground, and that will have an electric field that goes side to side, parallel to the ground. Can anybody take a guess as to what these different kinds of polarization would be called?
Magnetic.
Horizontal and vertical.
That would be horizontal. And the other one would be?
Vertical.
Vertical. And by and large, they don't matter a whole lot. Sometimes they matter an awful lot. When you're dealing with signals that bounce off the ionosphere, so let's say that I have my picture of the Earth and the ionosphere, and I have a horizontally polarized wave that comes up here. By the time it comes back down, it has a whole bunch of different stuff in it. It's been all turned around. So it's got a component like this and a component like this and one like that, which basically is known as elliptical polarization, which basically means that it's everything. There's some horizontal and some vertical thrown in there. Now, what that means also is if you're talking over long distances using high frequency, it does not matter what your antenna looks like, whether it makes a vertical or horizontally polarized wave. Doesn't make any difference at all. So now what we're talking about is we are talking about, let's go back to page 27. We're going to go to page 27, which is properties of radio waves and propagation modes. Okay, so now that we have specified what polarization is essentially the direction of the wire with respect to the ground. The electric field is going to be in the same direction as the wire, as the polarization is. So now what I'm going to do is erase this, and I'm going to say, okay, I'm going to have a vertical wire, which is going to make an electric field that goes up and down. What polarization would this be called?
Vertical.
Vertical. Okay. Now, let's say I have a second piece of wire, which is not transmitting, but there's an electric field that's going up and down. If a vertical piece of wire makes an electric field going up and down, what does an electric field up and down do to that vertical piece of wire?
It's gonna miss it.
No, it's actually, it's in the same direction. So if I had a signal that was being transmitted by this vertical piece of wire, if there's another vertical piece of wire, it's going to induce a signal on this piece of wire. If I have a vertical piece of wire that's transmitting a signal with an electric field that's going up and down, as soon as that electric field reaches another vertical piece of wire, it's going to make a signal show up on that second piece of wire.
Electron flow.
It's going to induce, yeah, it's actually going to induce a current on that second piece of wire, which is exactly what you want, because this would be the transmitting antenna and this would be the receiving antenna. That's exactly what you want. In other words, your transmitting antenna is putting out power and the receiving antenna is receiving it. And in order to actually get any energy from one place to another, the polarizations have to be the same. If I were to change this and make it so that my wire was polarized in this direction, and my electric field that it was looking for was this way, and the signal that came out of the first antenna was up and down, and I am looking for a signal that's side to side, how much energy am I going to get?
None.
None. That's right. So if I have a mismatch in my polarization of my two antennas, the first signal gets put out by one, and the second antenna, which is horizontal in this case, will completely miss it.
Are antennas horizontal? I thought they were all vertical.
For what purpose? If I have a piece of wire hung between two trees, here's a tree. If I have a piece of wire hung between two trees, which I do, what is the polarization of that antenna?
Horizontal.
That would be horizontal, right? If I have a house over here with a chimney and I've mounted a tower to my chimney, and on top of that, I have a vertical antenna, what would the polarization of that vertical antenna be?
Vertical.
That's right. So for
and
certain,
the height is always determining the frequency or wavelength it could get.
that's right. But I mean, I can have a horizontal antenna, like for instance, I can make that antenna, I can make that 250 feet long if I really want to. If I have a television, let's say a radio station, I can also have a 250-foot tall vertical antenna. They would operate at basically the same frequency, or they could be made to operate at the same frequency, but their polarizations would be totally opposite.
So the reason that you have both at your work home or wherever you said you had them is so that you can receive regardless of whether someone's transmitting vertical or horizontal?
Well, that's good. That's a really good question. So let's ask the next question. If I have an antenna for the 2-meter band, how long is 2 meters approximately?
2 meters.
Yeah, 2 meters. If I have a quarter wavelength antenna, it's a quarter wave long. That's about 0.5 meters. That's about 20 inches tall. Is there any point putting up an antenna that looks like that if it's 20 inches tall? Not really. I mean, I could, but basically what this becomes is an antenna that looks like this on top of the roof of my house. And it's only 20 inches tall. Now, here's the next question. Let us say that I was looking down at the roof of my house. Let's say that I was looking down at the roof of my house. What does a vertical antenna look like from above?
A dot.
A dot. Okay. So is there any asymmetry looking down at a dot?
Any asymmetry?
Yeah. It's a dot.
It's round, it's symmetrical.
It's symmetric. So is there any direction that is different from any other direction looking from the center of that dot?
All directions are the same.
That's right. Right, so there's signal going this way and this way and this way and this way. So in the horizontal plane, which is where most people live, right, on the surface of the earth, I am putting out and receiving an equal amount of signal in all directions if I have a vertical antenna. It doesn't have any preference. I could build an antenna that would have a preference, but I don't really want to do that because I want to receive everybody equally. Now, it also happens that above, let's say, 30 megahertz, when we start to get to VHF, you start to not worry about talking to people bouncing off the ionosphere because it's just probably not going to happen, in which case most of your communications are local. And if you're not bouncing stuff off the sky, your polarization does matter a lot because it doesn't get randomized. So vertical talks to vertical, horizontal talks to horizontal. They don't talk to each other. You know, the signals will basically just cross each other and they'll miss each other completely. So if I was building, let's say, a repeater station on top of a mountain and I wanted to have everybody anywhere able to talk to it, here's my repeater station. What kind of antenna would I put up? Horizontal or vertical?
Vertical.
Vertical. So that this station would be sending out and receiving signals equally well for everybody. Well, look what I have. I have the same thing. Let's say that I have a car over here with an antenna on it. Can you think of whether or not that would be an antenna that was horizontal or vertical?
Vertical.
Vertical, because it would want to receive stations in all directions as well. So basically for VHF and UHF, in particular, those are used for local line of sight communications. That's what handheld radios will typically talk on. They use frequency modulation or FM at UHF and VHF and UHF, and most antennas in use are vertical antennas. And that's exactly why. Now, if I were to look at the picture of my house from above, what I would see is here's my house, and here's one high frequency antenna, and here's another one. Because I have a tree here, I have another tree here, and I have another really big tree here, and another really big tree here. So what I've done is I actually have antennas that are horizontally strung up, very big antennas, between those trees. Because it doesn't really matter what signal goes out, whether it's horizontal or vertical. Now, what does matter is, as I'm going to erase this car, you notice that I now have an antenna that, are those antennas symmetric?
No.
They are not. They're symmetric in one axis only. What that means is, it turns out that they actually have preferential operation in this direction and this direction. Remember, I'm looking at this from above. I get nothing in the directions of those arrows that I just drew. This antenna will be preferential in this direction and that direction. This antenna will be preferential in this direction and this direction, which means that I have multiple antennas to cover all the different directions. I have
use that to specify in certain bandwidths or certain frequencies,
and I have them
Like
cut
a
for various different frequencies and bands. My feed lines that I use are such that I can actually use them on multiple different bands, but they also have different patterns that give me different coverages. And as I switch back and forth from one antenna to another and I'm listening to a distant station, it is usually true that one of those antennas receives a lot better than the other one does for that particular station, because that particular station might be over here. It could also be over here.
Do you do these multiple horizontal ones because you don't have space for a tall vertical?
No, I have space for a vertical. It's just easier to put up. It's easier to put up horizontal ones.
Oh, so it's easier to have a lot of horizontal ones than one.
Well, it
tall
depends. If I were putting up like a tower, on top of the tower, looking at it from above, I would have this. And I could rotate it.
Different spokes representing different frequency capabilities.
That's right. I would have, this would be a multi-band, a Yagi antenna, which has a maximum lobe in this direction. So I could basically just rotate. This is your old school, kind of like your old school TV antenna on a rotator, except that in this particular case, it's typically much bigger and it's got a lot more gain, but it's also designed for way different frequencies than your old school TV antenna.
In the horizontal ones, it looked like you were almost mimicking the finger displacement you were showing us on the axes, those three horizontals to capture different fields.
Yeah. Yep, that's why they're turned at different angles.
There's like a house in kind of a few blocks from my house that has just a gigantic antenna on it. It's kind of by Gillum Elementary.
Mm-hmm. I don't know who it is, but we could look them up. That's the other thing, it's easy to look things up. All right, let's see. So now that we've done a little bit of propagation, we're on page 27. VHF and UHF signals are generally known as line of sight, because line of sight is just like your eye. We know that UHF and VHF signals will cut through the atmosphere. They'll just go into space, which basically leaves us having something called line of sight communications. So they're not usually refracted or reflected by the ionosphere. So they're known as line of sight. Now, there's also something called the radio horizon. There's something called ground wave. And because we're left with signals that don't shoot and reflect off the sky, all of our terrestrial communications are line of sight or ground wave. Signals that hug the ground will actually follow the surface of the earth a little bit. The lower the frequency, the longer the wave, the more they'll hug the surface of the earth. So the earth, basically radio waves will travel a little bit further than light waves around the surface of the earth. It's still not very far, but they'll travel a little further. And that's known as the radio horizon. So this is actually really important. Now that we covered this thing called multipath, let's look at this from above. And we have a signal that goes this way and another one that goes this way and bounces off something and bounces back down. They get to this point having covered different distances. Does everyone agree with that?
Mm-hmm.
They covered different distances. Okay, so what if the path difference between the two is such that they went like this? You had one that came in like this and one that came in like that. What will you hear? If they cancel each other completely, you'll hear nothing. That's right. So what is one wavelength at, let's say, the 2 meter band? What's the length of one wavelength at the 2 meter band?
2 meters.
2 meters. So what happens if I were to now hear that I'm getting a lot of distortion and I move over a distance of 1 meter? And now all of a sudden, these things don't cancel anymore. They line up. What do I hear?
Whatever's being transmitted.
That's right. So it might just be, and I've noticed this a lot, you might move a couple of feet one way or the other on this particular frequency band, on the 2 meter band, and all of a sudden your signal will be good. And that literally you move around just a little bit inside a room. And if you think of that,
your cell phone.
well, yeah, actually it is. You can have cell dead spots. If you move 6 inches, it might be good again. And that's exactly why, because the signals will add rather than cancel.
How often does that really happen?
All the time. It literally is all the time, because radio waves bounce off of literally everything. You know, they'll get absorbed by some things, but they bounce off of everything also. Okay, what can happen if data signals arrive via multiple paths? Well, as you said, if you're sending If you're using a cell phone, what happens, Jan? What happens if you're in a bad spot?
You don't get it.
You don't get it. So your data,
Or you get it
your
broken.
error rate goes up, which means you don't get the data that you expected.
Mhm.
Okay, excellent. Okay, so if we're using a directional antenna, how can you access a distant repeater? Sometimes we can use this to our benefit. So let's say there's an obstruction here, and we know there's a building over here. We can actually take a directional antenna, which looks like this, and point our signal this way, and intentionally bounce it off of something. So you can actually intentionally bounce your signals off of things.
How do you know if it's going to absorb or bounce or be blocked?
You don't. You try it. Sometimes it might work and sometimes it might not. A lot of it depends on what it's made of. Now, you might also end up with something that looks like this, where you have a mountaintop and a person here and a person here, and they are not within communications range. So there's two ways to go. There's two ways to get past this mountain. One is to go around it, and another one, in theory, is to go over it. Every sharp object, and this comes back to physics, that's putting out, basically, if a wave gets to it, as soon as a wave encounters a sharp object, it will diffract. You'll have something going up and something going down and something going forward. And the stuff that goes down might actually get to where you intend it to go. And this is something that's actually, it comes from something called single slit diffraction. So this is actually a practical application of physics to radio. So, and that's known as knife edge. That actually has a name because it requires a sharp object like a knife, like a mountaintop, but basically something that is sharp, that has a knife edge, will cause diffraction that'll allow signals to bend around it. If you happen to be, as we drew, something like this, where you have a signal that's coming in from place to place and another one that's going like this, bouncing off of something, and they get there at a different time, well, the way to fix it sometimes is to move a little bit, right? But what happens if you're in a moving car? What will happen to the signal?
Going in and out.
It'll go in and out.
Yeah.
That is actually known as picket fencing. The reason being, if you've ever tried to talk through a picket fence as you're moving, what you'll hear is that you're open and then it closes. The signal goes away. And then there's an open path and then it goes away again. So that's actually known as picket fencing, and it's a very distinct sound. It's a rapid fluttering of the signal.
So Scott?
Yeah.
I'm not quite sure I'm going to articulate this correctly, but I'm, going back to the whole cell phone thing.
Mm-hmm.
If you're being told, I can't hear you very well, or you sound like you're underwater, or, which I get a lot with my phone.
Mm-hmm.
So what I've done is sometimes I'll walk out on my deck where I don't have walls all around me. And even sometimes we'll try to kind of put my phone up into the sky like that,
Yeah. That's actually because there's absorption of the signal in the walls of the house. I mean, you are basically looking to reduce your path loss.
Yeah.
Now, if you moved, say, hold on, okay, don't move from there, stay right there. Right? In other words, you found a good spot.
Mm-hmm.
That's basically what we're talking about.
Okay.
Because we're really looking at overall path loss, signal loss.
Mm-hmm.
Okay.
When you're doing the knife edge trick, when that wave goes up over and breaks at the sharp point of the mountain, does the wave refracting down, is it a whole wave or is it a bit?
No, it's going to be a very, very small portion.
Okay.
But one thing you'll learn is that sometimes you don't need very much. I mean, if you have a lot of excess signal going out in the first place, you don't need very much on the end.
Does that less amount of signal mean it's going to be lower volume, or?
Depends on the mode you're operating on. Because if it's AM or single sideband, yeah, you're going to have a weaker sounding signal. If it's FM, you'll probably you could have a little weaker sounding signal, but more than likely what you'll end up with is just higher static. So, and that comes down to the modulation that's being used, which is something I think we'll probably might cover tomorrow.
Can
It
you
might be tomorrow.
talk about the composition of that wave that can diffract into weaker things or stronger? I'm not getting a sense of how a wave can go on and parts of it be left behind. And
Okay, well, think of it like this. What do we know about energy?
a lot.
A lot. What do we know about energy? It can either be what?
Made nor destroyed.
You can neither create nor destroy energy. It has to go somewhere. This is called conservation of energy. And it's going to show up all over the place in stuff that we're talking about. So if I have a certain amount of energy that's going out and it hits something, right? Okay, let's say this is my let's say this is my wave and it hits a mountaintop or a building or something like that. And power is energy per unit time. That's the definition of power, right? So conservation of energy over at any given time also turns into conservation of power. So if I have 3 watts going out and it's making it to here, what does the sum of all of the energy or all the power that's being split apart and diffracted? What is the total that has to be coming out the other side?
3 watts.
3 watts, right? And it might be that I have 0.01 watt coming down this way. But if that is above the power level that will allow me to listen on the other side, then it will work.
So the wave that continues past the mountaintop is
The sum
weaker.
is the sum of all of them is is the other 2.99.
Yeah, okay. It's no longer what it was.
Right. Well, no, it's still the sum. Now, in reality, what'll probably happen is that this isn't 2.99. What'll happen is that you probably have, let's say 1 watt here, and then you have, being dissipated as heat in here, you have like the other 1.99.
The modulation carrier signal would still be intact, but of much lower amplitude.
Yeah. Exactly. Yeah.
So
The frequency doesn't change. Go ahead.
It was destroyed, but it was dissipated.
It was change. It would change form. Exactly. Let's get here. Here's the simple
Oh,
one.
it changed form. So you kept the heat went there, but there's still heat existed.
Right here. Let me ask this question. Take your hands and now rub them together. What happens to your hands?
Oh, they got a little warmer.
That's right. Okay. Well, the energy was converted from motion through friction into heat. Energy is energy, whether it's movement, whether it's a chemical reaction, whether it's an electrical thing, whether it's heat being generated. Energy is energy.
So it can't be created nor destroyed, but it can be converted.
It is always converted from form to form to form to form.
Okay. So that's what happened at the mountaintop.
Yep. And the same thing, like, okay, well, if I rubbed my hands together, what made the energy that was used for me to rub my hands together?
Chemical energy.
Chemical energy. That's right. I ate food. I ate food, which was converted into energy that the cells used to move my hands back and forth to make that energy. Right? And where did the food come from?
The sun.
Effectively, the sun. Yeah, effectively, it came from somewhere, which was the sun. So, yeah, I mean, basically, it's just moving around from place to place and form to form. Okay. Let's see.
But as a wave that someone else could pick up, it's now weaker.
Yeah, I mean, some of
Okay.
it's being burned up in other places.
Okay.
Okay. Let's see. Why might the range of VHF and UHF signals be better in the winter or be greater in the winter? And that's because what do we have between 2 points? If you live in the woods, you have trees. Trees have leaves. Leaves have water. As you fire energy through the leaves, through the trees, If it's summertime, you have more vegetation.
Mhm.
So that vegetation will absorb energy. The property of a radio wave used to describe its polarization, that's the orientation of the electric field. Electric field is either horizontal or vertical. If you have one vertical antenna talking to a horizontal antenna, those polarizations would be crossed and you'd have much, much, much weaker signals. For long distance weak signal, CW is Morse code, by the way. And for single sideband, which is SSB, for VHF and UHF weak signal work, you would typically use horizontal polarization. I believe that it's typically due to the fact that it will skip off the surface of the earth and off of water easier than vertical polarization, although I don't have proof of that.
Hey Scott, are you reading specific pages of the study guide now? Or what
Yeah,
are you reading off?
we're on the top of 29.
Can you start not for anything in particular? Can you just start every 5 pages? Just tell us what page you're on reading
Oh,
from.
yeah, okay.
Thanks,
Yep,
buddy.
29. Okay, so which of the following propagation types are most commonly associated with occasional strong over-the-horizon signals on 10, 6, and 2 meters? So what we're going to do is we're going to bring up this picture right here. And notice we have 10 meters, and we have 6 meters, and we have 2 meters. Well, 10 meters is usually in the realm of the daytime bands, especially when there's a lot of sunspots. And 6 meters is really when there's a lot of sunspots, which hasn't happened since 1957. 6 meters has not opened for F-layer propagation in 50-something years, 60-something years. 2 meters has also, it's virtually impossible for F-layer propagation to work on 2 meters. However, there's something called the E layer. Remember, we kind of glossed over that between the D and the F. There was this thing called the E. The E layer, it doesn't do a whole lot except when it does. And what it typically does is it builds up very, very, very thick layers of ionization for some strange reason. And it typically happens over, let's say, the southeast where there are a lot of thunderstorms. And thunderstorms are really low altitude, right? Well, those thunderstorms, it's thought, will generate very thick layers of ionization up in the sky in that E region. And what happens is that you can get VHF, this, like for instance, 2 meters, which is usually line of sight. This band can actually cover distances of 1,000 miles. The 6 meter band can cover distances of several thousand miles, and 1,000 miles at a bounce. So you might have a couple of bounces all lined up in a row and talk coast to coast on a band that's usually line of sight, which is very, very strange.
Is this where the astronauts are seeing those spritzing bursts on top of the clouds and thunder?
They're called sprites. It's
Sprites,
thought
thank
that
you.
those are actually doing it. Yeah. We can actually take signals, and what do we know about radio signals? What do they require to bounce? They require something in the sky that's built up, that being a plasma, right? Electrons floating around. Well, one of the most common sources of electrons floating around and ions floating around is the northern lights. There's also the southern lights. That's known as the aurora. And it's a very, very thick layer of plasma that forms up around the polar regions. And the same way that you can shoot signals up at the sky and have them bounce back down to the earth, you can actually shoot signals into the aurora and have them bounce back. They typically sound very distorted and fluttery because if you picture the aurora, you know, all the shimmering lights, that happens to radio waves when they bounce in and out too. But and that's known as auroral propagation. A meteor, when it travels through the sky and leaves a hot trail, that hot trail is actually ionization. It's basically generating a plasma because of the extreme heat. The 6 meter band is used to shoot signals off of meteor trails. Tropospheric scatter, that's in the lower levels of the atmosphere where we live. Essentially, tropospheric scatter is caused by random scattering of, so here's and here's the troposphere. This is where we are. Tropospheric scatter is that your signal tends to go up and it'll actually hit clouds and things and scatter off in all directions because it does hit things. So it's entirely possible that somebody 300 miles away can actually pick you up using something called troposcatter. There's another thing called an inversion layer, which is a temperature inversion. And what happens is if anyone's ever been driving a car and looked out over the highway and you see what looks like a reflection of the sky in the highway, it looks like a wet spot, but it's actually kind of bluish. That's actually a temperature inversion that's being caused right over the roadway because of the heat. And what that's doing is it's causing a different index of refraction to exist in that very small area. And what happens is the light comes down from the sun and it bounces up and down until it gets out of there. What it does is it makes it look like you're actually seeing a picture of the sky in the road. The same thing can happen up in the sky with radio waves, where you basically have a signal that's being sent from the Earth and it gets up into a temperature inversion layer and it changes the index of refraction and that signal bounces up and down until it comes out. Unlike being able to see the sky, this can actually be 2,500 miles long. The most common one is between Southern California and Hawaii, Northern California and Hawaii in the summertime, because you have a temperature inversion layer that forms over the Pacific Ocean. Microwave frequencies tend to get absorbed by precipitation. So this is actually an interesting question. We have this thing called a microwave oven, right? Anyone know what the original microwave oven was called? Anyone old enough to remember? A radar range. That's right. That's a radar range. And why was it called a radar range? If you think about it, why would anybody call this a radar range?
Use a magnetron with a radar frequency.
That's right. And actually it came out of testing right around World War II when people were doing radar. You'd send signals. Radar stands for radio detection and ranging. And you would try to bounce signals off of unknown things in the sky and measure how long it took and where those signals would come back. And you try to build a picture of it, right? Well, as it turns out, when they were doing radar range testing, they found that certain things, when they were sending them out at certain frequencies, would actually cause heating and it was determined that at certain frequencies, so here's the transmitting antenna. At certain frequencies, it would cause intense amounts of heating of water-containing products. Well, it turns out that the resonant frequency of water molecules is about 2.45 gigahertz. Well, it turns out that if you try to use microwaves and you shoot them toward trees, they'll tend to get absorbed. The same way that if you have a microwave oven with a cup of water, the cup itself won't get particularly hot, but the cup of water will get very hot because you're operating it at this frequency and you're using radio waves inside the microwave oven and you're heating up the water, which then I have to draw using red because it's now really hot. And that's the same reason why if you don't try this. If you try an uncooked egg and you throw it in your microwave, you'll make the egg explode because it heats the inside, but not the shell. Okay, so on other frequency bands, rain has no effect. It's really just microwave bands for that very reason. All right, is that enough for one day?
That's a lot.
That's a lot. But hey, normally, if I were doing a 2-day class, we'd have 5 more hours.
Woo!
Today.
A whole lot.
So, all right. Anybody have any questions?
Yeah,
I'm sure there are
did
some.
you send me that chart that you showed us 17 times?
Oh yeah.
Do I have that someplace?
I'll send that to everybody.
Are we utilizing the same Zoom link from
Yep.
tomorrow that we used this today? Okay.
Yep, same one every day.
And there's a lot here, Doc.
Yeah.
This is Larry.
Hi.
My sister's the one that texted you. But me, I'm not early.
Okay. Good. Good to meet you.
I enjoyed it.
Okay.
I learned something on that. I learned some stuff on that.
Okay.
You learned some things. I learned the thing today, so it was right interesting.
Excellent. Excellent.
I'll see you more on this thing on this thing channel, right?
Okay. Good.
I'll see you more then.
Okay.
Same time. All right. Bye.
Anybody else with any questions?
Scott, I may have
Sure,
missed
we've
the
got some.
attachments that were showing the different diagrams you had. When I looked in my email, I don't think they were attached. So if you send them again, that'll help.
Which email was it?
Merlin007@AOL.com.
Okay, there should have been an attachment in the same email that had the link.
Right, that's what surprised me when all of a
and
sudden those were there.
I wonder if it got stripped out.
Yeah, could you send
I
again?
think it's stripped out because I can't find it.
Right. I have an alternative email you can send to in case it did get stripped out.
Let me do that. Yeah.
All righty. When you're ready. Merlin00706.
Okay.
@gmail.com.
Email doesn't usually do it, so that's good. Okay.
Very helpful.
File. Okay. Let me.
Which file is this for?
It's for the whole big zip file of everything.
Gotcha.
Yeah.
Next time we start doing differential calculus, warn me.
Oh, we didn't do too much differential.
But no, I was just surprised to see it again. That's all.
Well, I mean, that was integral calculus, though.
Okay. Yeah, the integers time ranges. I forgot. Yes.
Okay. Let me grab this under radio, and okay, and I'll send it right now. Who else needed the packet?
Send one to me too.
Okay, let's hold on. It's a little slow. There we go.
Everybody, I guess.
Yes, everybody.
Well, if I send it to everybody, I don't want to send it to everybody. If you've already do you already have it?
Send it to Lois, please.
Wait, you don't have it?
Who are you talking to?
Lois.
I have seen it and I can't find it again.
I thought I resent it this morning.
Well, I can't find it now.
Okay, hold on.
I didn't see anything this morning.
I sent it at 9 o'clock. I sent it to Lois and Arnold.
Well,
you sent it to everybody at 9 o'clock?
No, I sent it to Lois.
Oh.
Specifically to Lois.
I didn't get it either.
Okay, who else doesn't have it?
I sent it to me too. I have a robust spam filter.
Okay, let's see, Doug.
Yep.
Hold on.
Send it to me too.
You've already got it. I know it was sent. You got it already, Larry.
Oh, all right.
Okay, Doug, is there a better email address?
No, that's good enough.
Well,
that's all the one I got.
Okay, it should have gone through, unless, like you said, the spam filter killed it. So,
well, I can go on the web and then find out if it's still there.
Yeah. Okay. Well, I'll send it again. Let me just grab it and send it.
I got mine back on March 19th.
Yeah. Well, right. I mean, it should have been as part of the welcome letter.
You sent something to me. It's got a zipper in it. Does that?
Everything's in the zip file.
Okay, and if I open that whole thing.
Yep.
So the whole thing, and to find the charts, let me see, use
There
band.
should be like 10. There should be like 10 files in there, and I'm going to send that. I'm going to send the picture of the spectrum out.
Oh, okay. All right. I appear to have it.
Okay, good. Let me make sure spectrum.
Yeah, the main email, it was an attachment. So some of you guys saw the links but didn't see the attachment.
Yeah, I've got mine.
Then you have to open that attachment to get it into it.
Copy. I'll send this other thing out right now.
Got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 PDFs in it.
That is correct. Okay, let's see. EMAG spectrum. Let me just open up my list. All right, any other questions while I'm doing this menial task? Because I can think while I'm doing menial tasks.
I've got mine.
Okay.
I was
have a
curious to
question
see
on
if you could
testing.
show me how to find like sort of antenna locations on maps. You said that that was all pretty searchable.
Oh, like where? Well, like where somebody is.
Ham licensing searchable.
Yeah. Hold on. Let me grab that. Let me just hit send on this. And I'm going to BCC everybody and do an email blast. And there were some people who I added this morning.
Keep in mind when they're licensed, they're not exactly searchable. You can't pinpoint an actual licensed user's exact location, but you
Right.
can dig up repeater locations throughout the US. You
Oh,
can
no,
dig
no,
up-
no. You can, I mean, it depends what somebody's been willing to give. If someone's listed themselves
Exactly.
with an
but
email
the-
address or with a mailbox, PO
with
box.
a mailbox, but like my mobile unit on my truck, if I'm operating
Well-
out of Utah, but my actual FCC license is in California, that's completely different.
That's true.
Yeah, my mobile unit on my truck, I can punch out 55 meters, but then like my actual home base setup is completely different.
Mhm. Let's see, Heidi.
Not
Okay.
that you know that, right?
Right. Okay, there we go. I just sent it out. All right. But let me share this. Actually, I'm gonna stop recording if I can remember where to find it.